all elements from sample space S2. What does it mean? In the case of tossing uh, a die and tossing a coin, that is what this example says. So when we consider tossing a coin as experiment 1 with sample space S1, then the elements of that experiment include head or tail, right? H comma T. When it comes to sample space S2, which includes the outcomes of rolling a die. So the sample space S2 contains the elements indicated by 1, 2, 3, 4, 5, 6. Okay. When I consider a combined experiment, that includes tossing a coin followed by tossing a die. Now my interest is to see the elements of combined sample space capital S, which is given by S1 cross S2, which is nothing but order pairs of elements from S1 and S2. When you see the elements of sample space, combined sample space, capital S, you will see that in the first ordered pair, which is shown by the cursor, I am trying to place the cursor as here. I hope you are able to see the cursor. So the first element of this ordered pair is H. When you see the second element is taken from sample space S2. Okay. So see the next ordered pair. The first element is same as H. Then third ordered pair. First element is head. Like that, the first six ordered pairs have got the first element as head. When it comes to second element, the second element is taken from the second sample space. The second elements are distinct in the first six ordered pairs. Now let us see the second set of six ordered pairs in the combined sample space. The first element of all the second set of six ordered pairs is tail. When it comes to second element for the second ordered pairs, the second element happened to be element taken from the sample space of second experiment 1, 2, 3, 4, 5, 6. Okay. Okay, that is what we mean by sample space, combined sample space. So in the previous class, we have considered an experiment where we have a set of elements which are continuous in nature. What does it mean? We have defined two events A and B. Event A is defined over sample space S1. Event B is defined over sample space S2. Okay. Combined event is defined as capital C, which is given by C equal to A cross B. What does it mean? S1 is subset of an element of A. Small s2 is an element of capital B, because A is defined over sample space S1, B is defined over sample space S2. Now this A cross B is an event in which the in which A cross S2 intersection with S1 cross B. A cross S2 is an ordered pair. S1 cross B is also an ordered pair of elements. When you consider the intersection of the two, we get a combined event denoted by C. So what does this first uh, set means? A cross S2. Take first element is taken from A and all possible elements are taken from S2. In other words, consider points of A, along with points of S2. Let us see in the form of a figure. Yes. So A is defined as an event where the element takes values from x1 to x2. B is defined as an event where the y coordinate is taking values from y1 to y2. So A is on x-axis, B is on y-axis. A is bounded by x1, x2, B is bounded by y1, y2. Let us see this. This is what in the previous class we are discussing. So along x-axis, I have event A taking values from x1 to x2, all possible values. Likewise, event B is defined over along y-axis taking values from y1 to y2. Now, what is A cross S2? So A cross S2 is a vertical strip. Okay, it is a vertical strip containing elements of A and all possible elements of Y. So the whole sample space. It includes all elements of sample space S2. When it comes to A cross B, S1 cross B, what does it mean? All elements from sample space S1 along with elements of event B. Event B elements are defined along y-axis with bounds as y1, y2. So in this horizontal strip, we have elements of B along with elements of S1. Okay. The intersection of these two strips, horizontal as well as vertical, that indicates A cross B. That is indicated by this portion. Okay. This is what we have seen in the previous class. Then once that is there, what is the probability of the combined event A cross B? Since we are considering combined independent experiments, the probability of A cross B is same as probability of A times probability of B. Okay. Then A cross B is also defined as, let me refer to the previous expression. A cross B is defined like this in equation 1.6-6. It is intersection of A cross S2, S1 cross B. So A cross S2 I will use here in this equation 1.6-9. A cross S2, S1 cross B. So probability of A cross S2 is nothing but probability of A into probability of S2. That is nothing but probability of A. Probability of S2 is nothing but probability combined sum of probabilities of all the elements. When you consider the whole sample space, the sum of the probabilities of the individual outcomes happening is 1. Likewise, in the second expression that follows, probability of S1 cross B is probability of S1 times probability of B. That is probability of B. That is how we compute the probabilities of events. So that is what we discussed in the previous class. Now, what is a permutation? What is a combination? You know, permutation is ordering of or elements taken from n. It is an ordering. Then combination is specific way of arranging the things. So yes, this is what is the basis for our present class. And today we see what is Bernoulli trial. By Bernoulli trials, it is plural, right? By Bernoulli trials, what we mean is repeating an experiment. How many times? Say capital N times. What type of experiment it is? It is an experiment that has got only two possible outcomes. Typically, tossing a coin. possible outcomes are head or tail. Then putting a question, did you have breakfast today? Possible answers, yes or no. Did you attend yesterday's class? Possible answers are yes or no. Likewise, did you uh, see the movie? Yes or no. Okay. Did you help your parents in any of household works today? Yes or no. Did you get up early today? Yes or no. Likewise, there can be a number of examples. Did you go through people's textbook, okay, covering the topics discussed so far? Yes or no. So all these are experiments. Putting a question is an experiment, and the possible answers are the outcomes of that experiment. If I ask you a question, did you understand the concept? You may say partially. That partially is the third answer. The two possible answers, other possible two answers are yes, I understood. No, I did not understand. Partially, I understood. So there are three possible outcomes for that question. So the sample space includes three possible outcomes, right? But we are considering an experiment where there are only two possible outcomes. What does it mean? If I assign the probability of occurrence of one event as small p, the probability of occurrence of the other event becomes, okay, 1 minus p. That is how we define um, the two possible outcomes of an experiment. Okay. Now, suppose the experiment is repeated capital N times, then A be the elementary event having one of the two possible outcomes. So here the idea is event one event is represented by capital A, so the other event becomes A complement. Suppose event A is defined as getting head, so A complement refers to the event of getting tail. If the probability of occurrence of event A is small p, then the probability of occurrence of event B or event A complement becomes 1 minus p. That is the advantage of considering experiments that have only two possible outcomes. Now, suppose the experiment is repeated how many times? Capital N times. For each trial, I will get one outcome. For each trial, I will get one outcome. So, when I repeat the experiment capital N times, I will get capital N outcomes. Now, the question is, my interest is to know the probability of getting exactly k heads, k times the event A should happen. What should happen in the remaining n minus k outcomes can be tail. Should be tail, right? So, if an experiment is repeated k times, and if the restriction is that, condition is that out of n outcomes, k outcomes should be heads or event A, then the probability of that event containing k outcomes of event A and n minus k outcomes of event A complement is given by, since the events are independent, I can take the product of individual probabilities. Probability of A into probability of A. How many times? K times. Because event A is happening K times The probability of occurrence of event is P of A. Okay. Remaining n minus k times A complement is happening. So the remaining n minus k terms are indicated by P of A complement. Okay. What is the probability of occurrence of event A small p? Okay. Then the probability of occurrence of A complement is 1 minus p. Now, since A is happening k times, p is raised to power k. Since 1 minus p is happening n minus k times, it is given by 1 minus p raised to the power n minus k. So, the probability of an event that includes k times event A, n minus k times event A complement is given by the expression or 1.7-3. Now the question is, how many times this particular combination is happening? So this particular combination is happening n c k times. How do I know? Out of n trials, event A should happen k times. That is nck. Nck is given by n factorial by k factorial times n minus k factorial. So the probability that A occurs exactly k times is given by the probability of nck, product of nck p power k, right, times 1 minus p n minus k. This is what the concept is. Okay. Then you see the 1.73 is the probability of this one sequence, only one sequence. How many such sequences? NCK sequences. Okay. There is an example in this textbook. Before discussing this example, I will discuss this with a general concept. Okay. The concept is Bernoulli trials we are discussing. So what type of experiment are we considering? We are considering an experiment, okay, that has only two possible outcomes. So event A is represented by one event is represented by event A and another event is represented by A complement. Since two events are defined, what are the combined probabilities? Probability of event A is P of A. Probability of event B is event A bar. Okay, is P of A bar. Okay. Now let me quote one example over here. Hmm. We all know the binary number system. Okay. In binary number system, how many distinct integers are available? Distinct symbols we say.
Two
How
symbols.
many, please? Two. Instead of distinct, let me put number of distinct symbols. What are those distinct symbols, please? Someone has responded, please.
0 and 1.
0, 1. Okay. How many possible, suppose I consider number of bits considered. I considered 3 bits. With 3 bits, how many possible combinations do I have? So let me write B2, B1, B0. Okay. 3 bits I have considered. What is the number of possible combinations?
8.
Number of possible
2 power 3.
combinations. Okay. It is 2 power 3. So what are those possible combinations? I am putting down those possible combinations. 0, 1, 0. These are all the possible combinations we have. Okay. So I should accommodate all the possible combinations in this space. Okay. Okay. Now my question is, in how many combinations I have exactly 1 0? Only 1 0. Okay. So I am putting this as 1. In how many combinations do I have exactly 1 0? This is one combination. This is another combination. Is it fine? So such combinations are 2. Next is, in how many combinations do I have only 2 zeros?
No, 1 0, 4 combinations are possible, right?
Yes, sir.
Only 1 0.
Yes, sir.
Okay. Oh, I missed. Right.
Yes, sir. 1 0.
Correct, correct. Here, one more is coming. One, one, one. Yes. Here, I think 3 only, right?
Yes, sir. 3 only, sir.
Okay. 3 combinations. Okay. In how many combinations do I have only 2 zeros? I am indicating those combinations by 2, 2, 3. That's all right. So 3. In how many combinations I have all 3 zeros? This is third combination. Only 1. Okay. So there is a combination in which all ones are there. That is 1. In our problem, in Bernoulli trials, the question goes like this. Requirement goes like this. Um, Consider a sequence where there is only 1 0. Order is not important. There is only 1 0 should happen. That means I should consider the first combination 1. Okay, this is what I need to consider. When I consider the case 1, I am considering case 1. In that case, how many zeros do happen? Only 1 0. Probability of occurrence of that 0 is represented by small p. Probability of occurrence of 1 is represented by 1 minus p. Now, since 0 is happening only once, what is the probability of that sequence? Probability of occurrence of 0. The other two occurrences are 1 minus p. So how do I write this? Probability of occurrence of 0 p, probability of occurrence of 1. How do I write it in formula notation? If I repeat the experiment 3 times, n equal to 3, out of those 3 times, only once 0 is happening. So p raised to power 1, that means p raised to power k 1 minus n raised to power n minus k. That is how the notations come up. Let me see the second one. Only 2 zeros. How many such see that combination? Only 2 zeros is indicated by
Sir, once
2.
again explain that first one.
Any question, please? Okay.
Can you
When I
please explain
consider
what's
only
happening
two
to it?
zeros, okay, let me scroll it up. Okay. Only 2 zeros. How do I represent the probability of that sequence? Only 2 zeros. So the third trial I should get 1. That is indicated by p square 1 minus p. When I consider the third case, only all 3 zeros. That means p raised to power 3, 1 minus p is raised to power 0 because n minus k is 0. I hope the concept is fine. Okay. Now consider this case 1 where only 1 0 is happening. How many such combinations do exist? Out of 3 trials, out of 3 possible outcomes, 0 should happen only once. How many? This NCK 3 by 2 factor 3 times, right? So when I see the number of possible combinations where there is exactly only 1 0, it is 3. Let me see the number of possible combinations where there are only 2 zeros. Okay. So how do I show that this is case 2 here? 3 factorial 2. 2 zeros should happen. So 3 factorial by 2 factorial again 3. How many combinations do I have exactly? 3 ones. It is 1. Okay. So when I put a restriction on the sequence, I should have the probability of occurring that sequence, probability of occurrence of that sequence that is given by this product. Next thing is how many times that event can take place. That is indicated by NCK. So finally, what is the probability of, okay, now, yes, what is the probability of 0 occurring only once? So I should show like this because 3 trials are there. P power 1, 1 minus p. Is it okay? This is what the concept behind Bernoulli trials. Any questions, please? I felt this is
Please
very
explain once
simple
again, sir, that
example.
formula of
So if there are no questions on this, let me refer to the
sir.
textbook. Yes. Now in this is what we are referring 1.7-5, the uppermost statement. Probability of A occurs exactly k times. Other words, probability of 0 occurs exactly 1 time or 2 times. Experiment is repeated 3 times or capital N times, out of which k is the number of possible times the desired event should happen. I hope 1.75 expression is clear. Now, in the example that follows, a submarine attempts to sink an aircraft carrier. It will be successful only if two or more torpedoes hit the carrier. If the submarine fires three torpedoes and the probability of a hit is zero point 0.4 for each torpedo, what is the probability that the submarine or the carrier will be sunk? Now, what is the experiment? Firing the torpedo. That is the experiment. What is the outcome? The carrier getting collapsed or sinking. So, in this experiment, hitting the carrier is an event. Other possible event is not hitting the carrier. So, there are only two possible outcomes: hitting, hit, or no hit. Okay. What is the probability of hit? 0.4. So, what should be the probability of miss or non hit? 1 minus p, that is 1 minus 0.4. How many times the experiment needs to be performed? The goal is to collapse the carrier. How many torpedoes should be fired? A minimum of 2 hits. So, the desired event is hitting the carrier. So, that is indicated by probability small p or 0.4. There can be a miss also. So, that is 1 minus p. Now, you see the steps. Probability that exactly no hits. 3C0, 0.4 raised to power 0, 1 minus p raised to power 3 minus 0. That is the probability of exactly no hits. What is the probability of exactly one hit? 3C1, 0.41 raised to power 1, 1 minus p raised to power 3 minus 1. Okay, let me show
Sir,
the, please,
so
please.
if exactly two hits, then we can't use this Bernoulli formula, no, sir, here.
Yes, what you said is right, but mathematically, we calculate the probability of no hit, probability of exactly one hit. It is only mathematical curiosity.
Okay, okay, sir. Yeah.
Logically, it continues, right? See how the concepts are getting developed. Suppose you have got some idea, you have studied your, say, circuit theory, diodes, transistors. So you visualized that a particular operation can be implemented using a particular circuit involving transistors, diodes. So, before experimenting, you should analyze the circuit. That is the normal process. While analyzing the circuit, how do you analyze? You take the basics. No? How does a diode conduct? How does a transistor behave for a given bias? So, from all those basics, you try to justify the working of the circuit you draw. Okay. If the working of the circuit proposed by you, okay, is in accordance with the basic things, then only you should experiment. Okay. So here also, actual event is probability of exactly two hits. This is what is required to be computed. Still, out of curiosity, I wish to know exactly one hit. What is the probability? Only it is only probability, right? Probability of exactly no hits. See, the last statement is probability of exactly three hits. Why to fire one more torpedo is wastage of effort, right? So that is how the problem goes. So exactly two hits means the desired event is hitting the aircraft carrier. So how many times we should hit? Two times. So small k happened to be 2, capital N happened to be 3. So 3 NCK. So 3C2, zero point 0.4 raised to power 2, then 1 minus 0.4 raised to power 1. Then exactly probability of exactly hitting 3 times. 3C3, 0.4 raised to power 3, 1 minus 0.4 raised to power 0. Okay. The answer we desire is C. Probability that the carrier should sink. Then probability of 2 or more hits. Okay. Then 2 or more hits means exactly 2 hits, exactly 3 hits. Okay, let me see the statement again. Problem. Uh, if the sub fires 3 torpedoes and the probability of hit is zero point 0.4 for each torpedo, what is the probability that the carrier will be sunk? But what is the condition? I am referring to the first line of the problem. It will be successful only if 2 or more torpedoes hit the carrier. So I should be worried about 2 or more torpedoes, right? It is not exactly 2. Earlier I thought only 2 hits the aircraft can be sunk, right? It is 2 or more, minimum 2. Okay. Beyond that is also recommended. I hope concept is clear. So exactly no hits, exactly one hit is out of curiosity. But two hits, three hits, and so on, they are more practical. Right? So probability that the carrier will be sunk is probability of 2 or more hits. Since the experiment is performed only 3 times, 2 hits exactly should be considered, exactly 3 hits is to be considered. So they are independent events, disjoint events, right? So probability of event 1 plus probability of other event. Is it okay? What I wish to convey over here is see the probabilities listed. Probability of exactly 3 hits is 0.06. Exactly 2 hits is 0.2. Probability of exactly 1 hit is 0.4. Probability of no hits is 0.2. Okay. See, out of these 4 probabilities, which event has got more value? That is probability of exactly 1 hit. That is what I understand. Okay. So can we infer out of this any feature? What I'm trying now is to note down those probabilities. That's all. Okay, what I'm writing is probability of no hits, that is given by point 216. Okay, then probability of exactly 1 hit, it is given by 0.432. Probability of exactly 2 hits, 0.288. Probability of exactly 3 hits, it is 0.0. 0.64. So after performing this calculation, just sum up the numericals. So just add up the probabilities. How much do you get? 4, 12, 18, 20,
It's
4,
one,
8,
sir.
10. No, please. Now sum of all the probabilities is 1. So we should get 1. That is very important. What does it mean? The sample space has got only these 4 combinations. Exactly no hits, exactly 1 hit, exactly 2 hits, and exactly 3 hits. So the sample space has got only these 4 possible outcomes. When I consider sum of all these probabilities, corresponding events probabilities, the sum is 1. That means I have considered all the possible outcomes. Any question, please? Someone has raised the question. Let me see. Anyone did put any question in chat? No. Okay. So if there are no questions, I will move to the next topic. There is one more example given in the textbook. Please go through that. This is what I am referring to. The second example is this example 1.7-2. That is followed by a formula. Okay. This is fine. Now, how to compute NCK when n is large and k is a small value? Say n equal to 100, k is 10. In such a scenario, we are referring to NCK, right? So how do we write NCK? This is what NCK is. Let n equal to 100 times the experiment is performed. My desired event should happen exactly 3 times whatever is the order. Then in this situation, NCK becomes 100C3. It is 100 factorial by, it is simple case, 99 into 98 by 6. Okay. Suppose k equal to say 20. When k is 20 with same value of n, what is NCK? It becomes 100 factorial by 20 factorial multiplied 80 factorial. Now computing this results in a large value. So what is being said is, here there are some simplifications being proposed. Now the probability that A occurs exactly k times is given by NCK multiplied by p power k into 1 minus p raised to power n minus k. Okay. This can be simplified to the expression given by 1.7-7. So we should remember that there is no other choice, right? When you see the terms, you see the first ratio 1 by square root of 2 pi np into 1 minus p. What is capital N? Number of times the experiment is repeated. What is small p? Probability of the desired event. 1 minus p is probability of the other event. So in the denominator, we need to have product of 2 pi n p and 1 minus p. That is how we should remember. Okay. When it comes to the terms in exponential, it is k minus np whole square. What is k? Number of times the desired event should happen. What is n? What is p? N is number of times the experiment is repeated. Small p is number of times the desired event should happen. So that product NP is one parameter to be considered when you see the denominator in that ratio 2 times n times p multiplied by 1 minus p. So this approximation, that's why here approximately equal to is indicated. This approximation is referred to as de Moivre Laplace approximation, and it holds for capital N, small k, and n minus k large. K near NP such that its deviation from NP, higher side or lower side, are small in magnitude relative to both NP and n times 1 minus p. So what does this mean? I am trying to explain that statement. So this approximation is to be used only when the condition that, what is the condition? K near NP. Now in the previous example I took n equal to 100 in one case, k equal to 3. Let me apply this. What is k? K equal to 3. K is near NP. Say probability of occurrence of desired event is say 0.4. 1 minus p is 0.6. Okay. What is NP now? NP equal to 0.4. It is 40. Okay. That is NP. What is K? 3. Now compare these two. When I compare K and NP, what the statement in the textbook says, K near NP such that its deviation from NP, higher or lower side, are small in magnitude. Where is NP? This is real axis. So all numericals are placed. Say 0 is over here. K, 3 is here. Okay. This is K equal to 3. Then what is NP? NP is 40. Probably 40 is here. What is N into 1 minus P? 60. Probably 60 is here. Such that its deviation of K from NP. What is the deviation of K from NP? This is the deviation of K from NP. So it is 36. That deviation from NP, higher side or lower side, are small in magnitude relative to both NP and N minus P. Small means, I will tell you one thing. 1 is smaller compared to 10, far smaller. 1/10 at least you should take. 2 is smaller compared to say 30. Because 1/10 of 30 is 3. So for when you consider a value less than 1/10 of this value, then this expression is valid. Now you see the deviation 36 and 40. So 36 is not smaller. So I cannot use this, right? So I should consider situations where this criterion is applicable, right? So one example is also listed over here. Let us see that example and try to understand this concept, right? So the example is, suppose a certain we are seeing the application of this Laplace de Moivre's approximation. Suppose a certain machine gun fires cartridges for 3 seconds at a rate of 2400 per minute, and the possibility of any bullets hitting a large target is zero point 0.4. Find the probability that exactly 50 of the bullets hit the target. What is the experiment? Firing a cartridge. Okay. Then at what rate? 2400 per minute. So 2400 per minute means 2400 by 60. That is per second we get. So 40 bullets can be fired per second. Okay? And the probability of any bullet hitting a target is 0.4, small p is 0.4, not hitting is 1 minus p, so 0.6. We find the probability that exactly 50 of the bullets hit the target. Now, what is capital N? How many times the experiment is repeated? The experiment is firing the machine gun. For how much time? For 3 seconds. When the machine gun has been used for 3 seconds continuously, how many bullets could have gone out? Per second, number of bullets that go out is 2400 by 60. For 3 seconds, it is 3 times 2400 by 60. Okay. So 120 bullets could have gone out in 3 seconds. So 120 attempts have been made. So capital N, number of trials is 120. That is how we should understand, right? Then what is the requirement? Exactly 50 of the bullets should hit the target. So the desired event should happen k equal to 50 times. What is the probability of desired event? 0.4. Small b is 0.4. 1 minus p is zero point 0.6. Now, if you want to apply De Moivre Laplace approximation, what things do we need to know? We need to know what is the value of capital N times p. Then what is the value of capital N times 1 minus p? The reason is k should be in the neighborhood of capital N times p. Okay. For that reason, we need to compute. So capital N times p happen to be 120 times 0.4, that is 48. Capital N times 1 minus p is 72. Since nk and n minus k are all large, while k is near np. How do we know k is near np? Small k here is 50, np is 48. See the spacing between 48 and 50. It is only 2 units. So k is near np. Okay. And the deviation of k from np, that is 2, which is 2, is much smaller than both 48 and 72. How do we conclude? Take 1/10 of np, take 1/10 of n times 1 minus p. When I take 1/10 of NP, it is 4.8. That 4.8 is on higher side compared to 50 minus 48, that is 2. So now I can apply the De Moivre's approximation. So this is how the problem is to be solved. First, we will write the expression taken from Bernoulli trials concept. After writing down that expression, we will write down the approximation. So 2 pi NP into 1 minus P. That is in the denominator of the ratio, first term. In the exponential factor, we will have K minus NP whole square by 2. What are the terms, please? 2, I2 did not remember. NP times 1 minus P. Okay. So NP is 48. 1 minus P is 1 minus 0.4. That is how we get the expression. Is it okay? While putting down the answer also, we will show the approximate equality sign over here. Then equal to for the final answer just before that. What the next statement is the approximation of 1.77. What is that? De Moivre's Laplace approximation. 1.77. This De Moivre Laplace approximation. What happens to that? It fails to be accurate when n becomes very large while p is very small. So p is very small means the desired event happening probability is say 0.001, such case, right? For these conditions, another approximation is helpful. It is called Poisson approximation. So this is how the Poisson approximation is to be considered. Replace the expression for Bernoulli trial by this Poisson approximation and solve the problem. N large and P small. Any questions, please? This is about people's. So if there are no questions, let me move on to the next. So sequence of problems, try to work out these problems. You can expect this one of these problems in your mid or my end examination. Okay, be thorough with all these problems. So when we meet again, I will be discussing the second chapter, that is random variables. Let me show that. Please work out all these problems. Don't leave any problem. This is what the topic for tomorrow's class, the random variable. Okay. This will be considered from people's text. Any questions, please?
Sir. Thank you, sir. Thank you, sir.
Okay, if there are no questions, let me close the session for today. Thank you for staying with me. Okay, uh, we will be meeting tomorrow again. Tomorrow the class is at 11:30. Thank you.